Good morning, everyone. Welcome to Demystifying the Secure Enclave Processor in Lagoon K. A couple notes before we get started. The business hall is in Bayside AB. Black Hat Arsenal is on the Palm Foyer on level 3, and the reception will be at 5 p.m. tonight. Visit the Kali Linux lab in Mandalay Bay A, and thanks for putting your phones on vibrate during the presentation. So we'd like to welcome David Wang, Tarjei Mandt, and Mathew Solnik.
Thank you. Thank you. Okay, can you hear me? Welcome to Demystifying Secure Enclave Processor. So there's 3 of us up here. I'm Mathew Solnik. We have David Wang and Tarjei Mandt. These 2 work at Azimuth. I used to work with them. Now I'm at Offcell. So a little bit of an introduction. A few years ago, Apple released their first 64-bit phone, the Apple 5S, or the iPhone 5S. Had a bunch of new technologies, one of which we're talking about today is Secure Enclave Processor. It does a lot of cool, interesting crypto stuff and some other things. So effectively, it is a core within the SOC that performs different secure operations completely separate from the main AP. Big one, Touch ID. And interesting thing as well is it has a full stack of OS apps, so on. So there's not too much public information outside of Apple's security guide, as well as our favorites, Apple's patents. If you want to learn everything, or as much as you can, read those patents. That's where we learned a lot. And but still left a lot of questions. A few of them are listed, but we're going to try to go through some of those. So basic outline. You can see up there, a big one is don't leave early because we actually go through the security stuff at the end. So, okay, let's talk a little bit about the hardware design. This is personally my favorite. So Apple SEP has a dedicated core. It's called the Kingfisher core. It's an ARM v7A. And what's interesting is it's completely segregated from the rest of the SOC. So if you own AP on EL3, it still does not give you any access to SEP itself. You know, it appears to be running at like 300 to 400 megahertz. But another cool thing is there's a bunch of other ARM v7 cores on the SOC, and those are not protected, and they're very similar to the actual SEP core. They make a great place to do research. And notice some changes between the different SOC versions, A7 through A9. It seems like the newer ones are more resistant to attacks. So SEP itself has a bunch of dedicated portions. So it has its own like crypto engine, its own fusing, random number generator, GID and UID keys. Those are completely separate from anything that's going on the AP. It also has a bunch of dedicated I/O that runs from the SOC, SEP part of the SOC, off it to the rest of the board, your iPhone board, so external peripherals can talk to it without going through AP at all. Now, while it does have dedicated items, it does share a fair amount with the AP. Big one is the Power Manager, which to me is really interesting because the security fuse settings are located in the Power Manager. And there's other neat things in there as well. Shares a memory controller that can be poked at from AP. PLL, so effectively the whole clocking of the chip, which again can be played with from AP. And has a shared secure mailbox, some piece of hardware that actually allows the 2 cores to communicate. And finally, shares external RAM. So let's talk a little bit about the physical memory. So it's got a dedicated boot ROM, like completely separate from AP, just like its own computer. Its boot ROM lives at the address listed. It also has dynamic inline encrypted AES memory, which is really cool. So if a attacker tries to do an off-SOC attack with the memory, it's still encrypted. I've never seen this before on a production SOC. It's really, really neat. And finally, it has a filter around this SEP core that protects it from standard attacks from AP. And only SEP has this. The other Kingfisher cores on the device do not. So let's talk a little bit about this filter. So effectively, you have this like wrapper around all of the important bits. So inside of it is the core, the GPIOs run into this, then it has mailbox, a few other things. But what's interesting is it's a one-way filter. So anything coming into it has to go through the mailbox. But anything going out or controlled via the SEP core can read all of physical memory. So if you're inside a SEP, you have full control of the device. But if you're outside a SEP, you have to, through physical design, go through this mailbox. And on to that, I'm going to hand over to David to do boot process.
So the boot process of SEP actually happens in several stages. The first stage is actually initiated by the AP. The SEP processor is initially held at reset. It's essentially stopped, and the AP boot ROM is responsible for starting the SEP. However, this process is irreversible. The AP doesn't have access to restart the SEP or to stop it. So the SEP actually uses 4 kilobytes of static RAM that appears to be inaccessible by the AP. Of course, and also it's on the chip, so it's less vulnerable to physical attacks. The problem with this amount of RAM is very small, but it's also enough to help it bootstrap into the next phase. It's so small that the SEP can't even put its page tables in RAM initially. It has to hard code its page tables in ROM. And the reason it needs page tables at all is because it uses large physical address extension, because the SEP itself is a 32-bit processor and it must address 64-bit physical address space. So after it's set up those two things, it starts a message loop. And I'm going to go over the details of how the SEP and AP communicate with each other in future slides, but suffice it to say that in this initial low capability state, not a lot of, it doesn't have a lot of capabilities. It can only generate nonces and get permission from the AP to continue to boot. Why does it need permission from the AP to continue to boot? Well, it needs to set up a protected area of, well, it needs to more than 4 kilobytes of RAM, so it needs to have access to the external RAM that it shares with the AP. And that RAM also needs to be protected from AP tampering with it. And that protection is actually partially configured by the AP. So the AP is allowed to configure 2 regions. One is called TZ0, probably trust zone 0. One's called TZ1. And TZ0 is for the SEP's use, and TZ1 is for the AP's hypervisor's use, which is involved in kernel patch protection. SEP can access TZ0, but the AP running in normal mode cannot access TZ0, nor running in hypervisor mode can it access TZ0. And TZ1, the SEP can't access TZ1, and only the AP in hypervisor mode can access TZ1. So the SEP must wait for the AP to donate a portion of its memory to it before it can actually continue the boot. So this is a diagram of how that boot flows. It's, of course, it's sort of a complicated dance between the AP and SEP because they're both responsible for parts of this configuration. What's interesting about this configuration is that even though iBoot is the one responsible for configuring TZ0 and TZ1, the AP doesn't actually send permission for the SEP to continue to boot until after the kernel completely starts up. So there's an interesting division there. There's a portion of time where the SEP boot ROM is vulnerable to attack from the iOS kernel. So SEP doesn't take AP's word for it that TZ0 is locked. Once TZ0 is locked, it's impossible to change the size and location of it. So first the SEP checks if TZ0 is locked from the hardware registers that it shares with the AP, and then it reads the size and address of TZ0 before continuing. So what happens after TZ0 is configured and SEP has its own area of memory? Well, actually, now it's protected against attacks from inside the iOS device, but what about someone with physical access? And Apple tries to mitigate that with memory encryption. So there's a separate memory encryption hardware that's attached to a SEP, and it appears to support these modes, but they actually use AES-256XEX. supports 2 channels, and how it works is pretty cool. You don't have to actually do anything special in software. You can just have the SEP core in software read memory from a certain address range, and you'll get it back in plain text, even though physically on the external RAM it's actually encrypted. And when you write in plain text, and it gets transparently encrypted, and it's actually encrypted on the physical memory. So how are these keys for memory encryption generated? Well, to summarize, a random number that is generated per boot is tangled or encrypted with a unique key to the device. So after all this is set up, SEP can finally move itself into the encrypted memory that it has set up. So it reinitializes itself, it reinitializes the page tables and clears the BSS and so on. And it begins a new message loop with no shared code between it and the initial low capability bootstrap. So afterwards, it actually retrieves certain information from the AP to continue to boot. On older iOS devices, they actually have an anti-replay token that's stored on AP's NAND that the AP sends over. But in all cases so far, the SEP actually receives its firmware per boot from the AP. So people sometimes talked about online about updating the SEP firmware. There's really no conception of that, because in actual reality, the SEP gets its firmware fresh from the AP on every boot. And now Matt will talk a little bit about how that SEP firmware is loaded.
Thanks, David. So yeah, we will talk, try to move this slide, talk a little bit about how the actual firmware is loaded from AP to the SEP core, and we'll talk about the actual format. So on 64-bit devices, Apple introduced what's called the Image4 format. It's different from the proprietary of Image3 in that it's pretty much just ASN1 during coding. It's also very similar to what's happening on AP's iBoot or BootROM and a couple other places, and can be parsed pretty much with any standard ASN1 parser. So in it, there are typically 2 to 3 major pieces. There's the payload itself, which is the big encrypted SEP firmware blob. There's a restore portion, which just has a couple basic information on restore. And there's the manifest, aka the AP ticket. Now for SEP, that is effectively the alpha and the omega of configuration and security. Okay, so let's talk a little bit more about the manifest, aka AP ticket. So effectively, it has a bunch of information about your device, your ECID, your actual chip ID, things like that, to only allow it to run on your specific device. So you can't take one firmware and run it on another. But some interesting things we've found, it has some settings that can be changed. They actually change the configuration of the OS as well as the hardware. A couple of those were the demote security and demote production flags. So let's talk a little bit about actually how this works. How do we reverse something that is not visible? Well, let's try to find some code reuse. Well, we can't necessarily see it. We can get an idea of how it works by looking at other areas that actually use Image4 parsing. So let's start in the most accessible place that's close to SEP, iBoot. Well, there's not symbols in iBoot, but we did find one string. Image4 decode copy manifest hash. And one string is all you need. So now that we know of this Image4 decode string, where else can we find it? Well, inside of the SEP util itself, which is used to send firmware, is this symbol as well as a bunch of others. Effectively, it's a full userland Image4 parser. That gave us a lot of information, and combined with some fun Googling, found that this is based on the libdir ASN1 parser that Apple actually releases open source. So got a bunch of fun information from that. And in addition, the RSA portion, the PKI, is done by Core Crypto, which, while not fully open source, is reviewable. So now we have a pretty good idea of what the actual Image4 parser is doing. So let's talk about how the flow works. So originally, AP sends the firmware over to SEP. Then it initializes the decoders, so has your payload, manifest, things like that, just kind of reads through those, verifies the digests, the certificates, make sure it's actually signed correctly. The root of trust of it all is actually in the boot ROM, so that certificate's not changing. Then after that, it goes through, verifies all the different properties in the manifest, make sure that the ECID matches, things like that. And finally, if all items pass, it executes the firmware itself. So this is just a basic overview. As you can see, just gets sent from AP to SEP, goes through each stage of verification. Once all the basics are validated, goes down to validate the certificate, and finally the properties against the hardware. What's interesting on this is it reads the fuses of the different security fuses to verify what settings are allowed in the manifest. So that's kind of an intro and what's going to be coming up later. On that, we will pass it over to Tarjei or David for the communications.
Right. So I'm going to talk a little bit about how AP and SEP communicate with each other. And basically, this is done by a piece of shared hardware between them called a secure mailbox. And it has an inbox and outbox register. And even though they share, it looks a little bit like shared memory, it actually behaves more like a FIFO. So how it works is that when the AP wants to send a message, it will write to the inbox register of the mailbox. And this generates an interrupt on the SEP side. And SEP is waiting for that interrupt. And when it gets it, it will read the inbox register of the mailbox and get the message. When the SEP wants to send a reply, it will write a message to the outbox register, which will generate a corresponding interrupt on the AP side. And the AP will then be signaled to read the message from the outbox register. So this is a chart that's very much like a chart on one of the Apple's patents, and it just illustrates that the mailbox mechanism and the filtering mechanism seem tightly interwoven. Especially since, when the AP tries to read an address that's not the outbox register, the filter responds to it with what Apple calls nonce data, which in practice is just all zeros. So this is the actual format of the message. Since the inbox and outbox registers are both 8 bytes in size, each message is only 8 bytes in size. And depending on the endpoint of the message, the destination endpoint of the message, they can have different formats. But there's only one constant in the formats, and that the first byte must be the endpoint index or endpoint number. But a lot of them have this format that's on the screen right now. And this is because the purpose of a lot of these endpoints are to serve as remote procedure call servers. So because the AP usually wants the SEP to do something. So there's a field called tag that identifies a session ID and opcode that identifies what the AP wants the SEP to do. And there's a 4-byte data payload at the end. So a lot of this functionality, communication functionality, is implemented on the AP side in the kernel by this kernel extension called Apple SEP Manager. And it provides a generic framework for drivers to communicate with SEP, and it labels different drivers to register as SEP endpoints. And it also has its own endpoints, and one of the most important endpoints is the control endpoint. And this is a list of some of the endpoints that are there. As you can see, the Apple SEP Manager kernel extension is responsible for a lot of them, but there's also other drivers like the key store, like the Apple key store, which manages passcodes and so on, that uses this functionality. And then you have some other endpoints like the stuff for the fingerprint sensor and secure element. So control endpoint, as I said, it handles control requests issued to the SEP, and it's used to set up request and reply out of line buffers, which I will talk about in the next slide. It also has some other functionality, and like generating, reading, and validating nonces. And also, you can sort of mess with it with SEPUtil, which is included on production devices. So if you have a jailbroken phone, you can play with the control endpoint. So here are some of the opcodes that the control endpoint supports. As you can see, it can you can set up addresses and sizes for these out-of-line buffers. So what are out-of-line buffers? They're an important part of communicating communication between the AP and SEP. This is because if your message size is only restricted to 8 bytes, then to send, for example, even the SEP firmware will take a long time. So because the SEP can actually access anywhere in the AP's memory except for the memory in TZ1, the SEP can just directly read and write information to that memory. So the out-of-line buffers allows the AP to assign certain buffers for the SEP to do that. So the control endpoint is used to assign the request and reply buffers to any endpoint. And this is done during endpoint registration. So this is a diagram of how that flow works. If there's an out-of-line buffer required for a particular endpoint, then the kernel will allocate some physical memory and register that physical memory address by sending it over the EP0 for the send buffer and then also for the receive buffer. So with this RPC mechanism, a lot of the drivers that used to be exclusively in the iOS kernel have now been moved to the SEP. And the drivers themselves, what used to be Apple Key Store is now renamed Apple SEP Key Store. What used to be Apple Credential Manager is now named Apple SEP Credential Manager. And these kernel extensions are merely stubs that just call into the corresponding application in the SEP using that communication mechanism. And now Tarjei will talk a little bit about the details of how SEPOS works.
All right, thank you, David. SEPOS. SEPOS is actually an entirely self-contained operating system. It's based on L4, which is a microkernel. So a microkernel is basically just a very small kernel with a very small set of interfaces where the major portion of the operating system is implemented in user mode. It was introduced in '93. A lot of the microkernels at the time were pretty slow in terms of IPC, and IPC is super important in microkernels. So L4 was sort of a milestone at the time because it improved the performance considerably. Since its introduction, there's been a lot of different implementations and variants, notably L4 embedded, which was targeted for embedded devices. So SEPOS is actually based on L4 embedded. It has a lot of custom modifications made by Apple, including its own drivers, its own services, applications. It's also, all of these applications are compiled as mockup binaries. And the kernel itself, like I said, only provides a small set of interfaces, like a small set of system calls. So the major part of the operating system is implemented in these driver services and applications. So this is an overview of the SEPOS architecture, where on the top you can see all the applications. The layer below has the core SEPOS components with the drivers, the services, the libraries, frameworks. Also, there's a special task, a root task called SEPOS, which has a Bootstrap server. We'll go more into detail on all of these. Below it, you have the embedded runtime, which is a library that it uses to interface with the kernel itself, and the hardware. So the kernel basically just initializes the system, brings it up to a state where it becomes usable. So this includes like setting up the page table, the kernel interface page, starting the timer, starting the scheduler, and the kernel scheduler actually starts the initial task, the root task. The L4 kernel also provides a very small set of system calls, about 20, and these system calls are then used by the root task to create more sophisticated services, like having a sort of a memory management system, a way to do more complex things. So if you're familiar with L4, these are a lot of these system calls are very familiar. So most of the system calls in SEPOS are actually the same you'll see on any L4 implementation. So these are, just a few. Because a lot of these system calls are powerful, L4 has this concept known as privileged system calls. So only the root task in SEPOS the most privileged task can invoke these system calls. And this is determined by each individual system call by checking the space address of the caller. So when you invoke a system call, it may call this privilege space function in order to check the privilege. And an example of this is shown here. So this is the L4 space control system call from the Darbat source, where it then checks if the caller is actually privileged. So you can't just, as any application, you can't just go ahead and call these. You will need to do IPC to the root task, the SEPOS task, to be able to invoke the functionality you need. So SEPOS, the root task is, well, it's kind of a bit confusing because it's called the same name, but it's actually the initial process on boot, and it can basically call any privileged system call. Its job is just to start all the applications, and then it also maintains a context structure for each task. So it basically has information about the virtual address space of all the applications, their privilege level, their threads, etc. And once it's done this, it also invokes a Bootstrap server. So the Bootstrap server provides all the services applications rely on. So this is a chart just illustrating the app initialization process. So in the first step, it basically reads the application list from the SEP firmware, and each entry in this list has information about how it's supposed to load. So it goes through the step of creating an address space for the process. It parses the headers of the Mako binary, and then loads the segments, and finally it starts the thread for the main thread. Once it's done this, it actually also computes the CRC of all the loaded images in memory, and then checks that against a CRC that's been pre-computed. And then if that's okay, then it continues to boot. If not, it will fail. So the application list briefly just contains a list of all the applications, with the virtual base address, the module name, size, entry points, etc., and it's located at a fixed offset in the SEP firmware. So it actually looks like this. So this is like the raw data, and as you can see, it has names on the right: SEPOS, SEP drivers, SEP services, and then offsets where it's supposed to find this in the firmware. So the Bootstrap server is probably the most important piece in SEPOS. It implements all the core functionality. It provides a number of tables with methods supporting like system, thread, object management. When I say object, I mean memory management. So you create an object and then you map that object into the memory of the application, and that basically sets up a virtual memory mapping. In order to communicate with the Bootstrap server, you use the embedded runtime to call this ERT RPC Bootstrap server function, and that basically just gives you a handle back or a thread ID to the Bootstrap server. So then you're able to invoke functions. So for instance, in order to create a thread, so a thread create system call is privileged. So you would then call the Bootstrap server in order to do that for you, and it would give you a new thread. Since the Bootstrap server also exports a lot of different methods, it also has the concept of privileged methods. So only a certain set of application can invoke these methods. Examples of privileged methods are the ability to query information about, for instance, objects, processes, mappings, etc. And they have a kind of interesting way of determining whether a process is privileged. Actually, if the first 4 letters are uppercase, then the process is considered a privileged process. So it's kind of interesting. And in order to check that, they have a function called proc has privilege. So each individual function, for instance, this function, which supplies you with ACL info, will call this function in order to determine if the caller is privileged. The sender of the RPC request is privileged. Some functions also are very powerful. So they are essentially, some functions allow you to map arbitrary physical memory. So in these cases, processes are assigned, or applications are assigned specific entitlements. And this is done by checking a table whenever a process is launched. So examples of this is the SEPOS object create phys function, and also the remap function, which allows you to remap a virtual to physical mapping. So this is just a pseudocode representation of the proc create function in the root task. So basically, when it does the create, it will use the name you give it and check against the database or a table. And if it's in this table, it will assign these entitlements to that running application. So in this case, there are 3 different entries. It's SEPD, RTM, and debug. And they're assigned different values like 2 and 6. So this is basically SEP drivers, Art Manager, and debug. And the entitlements are the map phys entitlement basically gives you the ability to map physical memory, and the map SEP entitlement basically gives you the ability to map a certain portion of SEP memory. Besides the Bootstrap server, we also have drivers. So all the drivers are hosted in their own application. So all drivers are implemented entirely in user mode. You can do low-level driver operations because the drivers map IO registers into the application address space. And applications like SEP applications can interact with these drivers through the driver API. So the driver API basically just interacts over RPC with the SEP drivers process. It doesn't talk immediately with the SEP drivers process because it doesn't have a handle. Instead, it will look up the SEPD service with SEPOS task and get a handle back, and then it can do a driver lookup and get a thread handle to the actual driver it wants. So perhaps the most important driver in SEPOS is the AKF driver, presumably the Apple Kingfisher driver. And it manages the AP SEP endpoints. It also handles the control requests. So when David talked about out-of-line buffers and sending those buffer addresses to EP0, this is actually what sets up that on the SEP side. SEP applications can also register their own endpoints, so they can do that at runtime as well. Besides drivers, there's also SEP services. So SEP services is basically just leveraging the functionality of drivers and implementing their own set of interfaces, so called a service. So this is like another way of exposing more general things to applications. So examples of this are listed here: the key generation service, the anti-replay service, etc. These can also be interacted with their own API. So you have a service lookup API, a service call API, and it works pretty much the same way as the drivers, where you talk to SEPOS, get a handle to the services application, and then you call service lookup in order to get the service you want, and subsequently use service call. Finally, all the applications, they're primarily designed to support the kernel extensions that run in iOS or perform specific operations on behalf of those kernel extensions. Some applications are also only specific to a certain class of devices. For instance, Apple Pay, and you saw the debug application earlier. So that's not actually on production devices. We have not seen that. So some are exclusive to, for instance, development builds. So that was just like a introduction to SEPOS, and now we'll move on to the more interesting part, which is like what is the attack surface of SEPOS. So in terms of software, it mostly comprises the methods that we use to communicate from AP to SEP. So the methods, so these methods basically boil down to the mailbox and the shared request and reply buffers. In order to carry out attacks, we sort of assume we have kernel privileges in iOS because we need to be able to write arbitrary messages to the secure mailbox. So every endpoint in SEPOS, the AKF endpoints, is actually considered a target because all these endpoints they handle the messages we send. So this includes all the drivers, all the applications. It does not require a corresponding driver to be registered in iOS because we can just write directly to the mailbox. So we basically are just interested in which AKF endpoints are registered. And these are the register endpoints. So it's about 8. We have the control endpoint, but we also have a lot of other endpoints. And this table also shows which of the endpoints actually makes use of the outer line buffers. So which endpoints will parse data out of line, presumably complex blobs of information. So this is just an example of an endpoint handler. So this is the SEP biometrics message handler. And as you can see, it's very complex. It has a huge switch statement with supporting a lot of opcodes. So assuming we have a vulnerability, for instance, in one of these handlers, how much effort do we need to spend to exploit a SEP vulnerability? This is basically just a standard way of thinking when you exploit vulnerabilities. It's determined by several factors: the randomization of the process address space, any allocator heap hardening, any exploit mitigations present, if it, stack cookies, etc. So the address space layout of SEP application is very static. Like there's no image-based randomization at all. Every application is typically based at 1,000 or 8,000 hex, depending on whether it has a page 0 segment. And page 0 segments are actually ignored by the loader. So there's really no null page protection. But then again, you can't really map to null page unless you have control of the root task. So it's not a big deal, but it's still interesting. I think this crashed.
Machine crashed?
No, it's not responding. It's just working a lot. Oh, there you go. It's loading the image. All right. So in terms of stack corruptions, we're interested in how the stacks are allocated and where they're put. So the main thread of all the SEP applications use an image embedded stack. So this actually means that stack is in the data segment. So if you have a stack recursion vulnerability or a stack-based buffer overrun, you essentially end up corrupting adjacent data. That said, additional threads will not have their stacks in the data segment. They'll have their stacks allocated at runtime using objects. And objects are actually padded, so there are gaps between them with empty, like they're not out. There's empty space between them, so that will trigger a seg fault. So essentially, these stacks have guard pages, but yeah. SEP applications, they have stack cookies, but obviously when you fix the value to GARD, the stack cookie is not very robust. Stack addresses are in most cases known because, as we saw here, the main thread stack is inside the image of the loaded application, and the loaded application does not have randomization, so you immediately know the address of the main thread stack. And furthermore, the addresses of the other thread stacks are also very trivial to compute because the memory layout is very predictable. In terms of heap corruptions, we are interested in how applications allocate memory, how they dynamically allocate memory. And the runtime allocator in SEP applications is a KNR implementation. So whenever you call malloc, it uses this implementation. This is a very simple allocator. It just has a single free list ordered by size. And the header has just a pointer to the next free element and the block size. The size of the heap is actually determined on when you start up the application. So it calls this malloc init function. This heap is actually non-expandable. So you just give it a parameter describing the size of the heap, and then that's your heap for the entire lifetime of the application. This is just showing you the free list. So it's a very basic allocator where you have used data, free data, and when it's in use, it still has this metadata. So, of course, there's no protection of heap metadata here. The free list pointers, then you can easily overwrite them in order to corrupt arbitrary memory. You can overwrite the block size to extend the corruption of an existing heap corruption. Moreover, like the malloc area that are assigned to these applications are also in the data segment. So every malloc is at a predictable address. Also, the allocations are made in predictable order, so it's very easy to predict where they're allocated. Finally, SEPOS actually does something a lot of L4 implementation does not, support XN and PXN. So it actually, whenever a page is not explicitly marked as executable, it sets these bits in the page table entries. It also sets the non-secure bit for all pages outside the SEP memory region. So this is a mitigation summary of SEPOS. In some regards, it does offer some protection, but in most cases, like address-based layout randomization, heap metadata, stack cookies, it does not really meet up with the modern operating system trends we see today. So Mathew will talk a bit more about the attack surface on the hardware.
Okay, yeah, so let's talk a little bit about attacking boot ROM. Boot ROM is a pretty interesting place, but it does not have a huge attack surface. There's pretty much two major spots. One, you have the image for parser, so you've got like standard memory corruption as well as potential logic flaws. The other is purely hardware-based attacks, or some sort of combination of the two. So boot ROM itself doesn't really have very much on anti-exploit mitigations. It's a boot ROM, but it does have some basic stuff, so it's got a basic stack guard. Only issue though is one decent bug, and it's game over. So let's talk a little bit more about attacking the image forward parser. Now, ASN1 is a really, really hard thing to do right. There's been multiple vulns across pretty much all of the ASN1 parsers, some pretty big ones lately. Now, on the other hand, libdir itself, as you can see, it was designed with a very simple methodology. It doesn't do copies, doesn't do malloc, it just decodes. So it's actually really strong, and props to that. Though all of the code around it may not necessarily be as strong. Recommend do some auditing on that. So the next part, let's talk about directly attacking hardware. There's a few ways in. One, you have all of these peripheral lines going to off-SOC, chips. So, SPI, I2C, UART, those all have receivers that could potentially be exploited, not only in boot ROM, but also in the SEPOS itself. You could do standard side channel and differential power analysis if you have your keys. My recommendation, if you're going to try that, stick to the A7. The newer ones seem to be stronger against those. And then finally, more advanced glitching attacks. Standard clock, voltage, as well as others. So we'll talk a little bit about attacking the RAM itself. So while it is encrypted, the RAM is not verified. So if you do try doing different, say, physical attacks or even something like a row hammer attack, you can flip bits in RAM. So that can potentially affect the performance or affect how the device is running. Another portion is that the random part of the key generation is actually temporarily stored in unencrypted RAM. So if you're able to control that, you can effectively control how the key is generated. So finally, let's get a little bit more advanced. If you do want to do some interesting things, you could potentially attack the fuse array itself. It's one of the most invasive vectors, potentially, depending on where you go. Requires a lot of patience, and if you're like me, you're going to break a hell of a lot of devices. Now, some advanced people probably have like nice laser setups. Those are expensive, hard to use. If you are going after this, the two major things I would recommend is looking at the production mode and the security mode. So why exactly would you want to go after that? JTAG. So how would we necessarily get to JTAG? Well, you could say get a really big socket and start hitting the fuse array. How would we do that? Well, there's a really interesting pin that can be found called the fuse source pin. I'm not 100% sure of the reason for it, but it seems to run right into the fuse array. Though, if you're trying this, you would need to deal with like the CRC on the fuses, as well as this like thing called fuse sealing. Now, if you want to go a little bit easier, attack the image forward parser. Now, my question for the Apple people here, what exactly do dsec and dpro do? And on to the conclusion. So, SEP itself, SEPOS, was designed with security in mind. It's definitely very obvious. They've got like mailbox interface, privilege separation. Now, the OS itself was designed with some lacking some basic anti-exploit mitigations, things that most OSs have had for a long time. No memory layout, no static stack guards, things like that. And the actual applications in there have a pretty big attack surface. So while the overall attack surface is small, these applications present some interesting targets, especially the secure bio that we showed earlier. Finally, more on the hardware side. Now, the actual hardware itself is light years ahead of any of the competitors. I've never seen something so advanced. It's like the hardware filter, inline encrypted RAM, and generally a really small attack surface. So I've got to give props to the Apple hardware team. They did an awesome job, and they really should talk more about it because that's like some of the coolest stuff I've ever seen. Now, while they did do a really good job, there are some weaknesses, probably due to cost and battery life, but the weaknesses are it does have a shared PLL and shared power manager. Considering the security fusing is in the power manager, may not be the best thing to share. They have this interesting fuse source pin running on the SOC. Probably should reevaluate that. And finally, the demotion functionality does seem kind of dangerous. Why exactly does JTAG over Lightning even exist? And in the end, I want to address one thing before saying things. The white elephant in the room, how exactly did we get in? Well, good to ask us next time we talk. So, and thank you to Ryan Malone, Daniel Borka, and our anonymous reviewers. And we have some bonus slides, but those will just be in slides online. So, and we're done. Oh, and thank you to the Apple team for a really interesting target.